Hello everyone. In this video we would be talking about the 10th chapter, that is magnetism. To understand magnetism, first let's try to understand and define magnet. Magnet is a material that produces magnetic field and attracts other magnetic material towards itself. Now the phenomenon is known as magnetism, and magnetism can also be produced by electric current. That how it is being produced by electric current and things like that we are going to cover up in the second part of this chapter, where we will be talking about electromagnets. So to start with, as you can see here, that it was first found as lodestone, which is an ore of iron oxide Fe3O4 in magnesia. Now it possesses two characteristics. They are basically that it attracted small pieces of iron, and the second characteristics which it possessed was it sets itself along a definite direction when we suspend it freely with a silk thread. You can see this figure here. When it's suspended with the help of a silk thread, then it is suspended along north-south direction. So these are the two properties of a magnet we have to keep in mind. A magnet has two poles, north pole and south pole. Please remember that like poles will repel each other and unlike poles will attract each other. Now, if we have a magnet, let's say, which has got two poles, and what we do is we break the magnet, then what happens is we get two smaller magnets, and both of them will have their own north and south poles. If two opposite poles come together, there will be a attraction. If similar pole comes together, that is NN or SS, that is north pole and south pole and south pole, they will repel each other. Now next topic is induced magnetism. To understand this topic, let's focus on this figure. Suppose we have a magnet. These are the two poles, the north pole and the south pole, and we bring a iron or steel bar and keep it next to the magnet. Then after a certain time, this iron rod will start behaving as a magnet. And how is it proved? Because it will start attracting these small iron fillings. Now this bar was not a magnet, this was an iron bar or a steel bar, but it has acquired the properties of a magnet. So this entire phenomenon is known as induced magnetism. When you place a magnet near an iron or steel bar, and then that iron or steel bar also starts behaving as a magnet, that is known as induced magnetism. This is the definition. The temporary magnetism acquired by a magnetic material when it is kept near or in contact with a magnet is called induced magnetism. So please put a star mark to this point. And a magnetic pole induces an opposite polarity on the near end and a similar polarity on the further end of the iron bar. This is what we have seen here. This was south pole, so here it was induced north pole. Otherwise they will start repelling each other. Now induction precedes attraction. So this is when, in the previous case, when we saw that this iron bar started to attract the iron fillings, first this iron bar was converted into a magnet. There was an attraction. So this is what they are saying here, that induction precedes attraction. And the second thing is induced magnetism is temporary. To understand this, they have given us this figure. Now there is a magnet this is the south pole and this is the north pole. Then we take a pin, maybe an iron pin, and we find that this pin is attracted to this magnetic bar. Now this part of the magnet is north pole, so the part of the iron nail which is near to the north pole develops the opposite polarity, that is south pole, and this other part becomes north pole. Similarly, another pin is brought near to this iron nail, and here we find that since this is north pole, so the tip of this iron nail becomes south pole and the chain continues. But this will remain, or this iron nail will behave as a magnet only till we have this magnet kept near to this iron. The moment we remove this bar magnet from here, then all these iron nails will lose their property of magnetism. So we say that the magnetism acquired by them is purely temporary. To understand the lines of the magnetic field, if we have to go through the definition, then it is the space around a magnet in which if you keep the needle of a compass, then it will rest in a direction other than the north and south direction of the earth. In simple words, if we have to understand the magnetic field lines, this is the area till where we feel the effect of the magnet. We have to remember, please put a star mark here, and we have to remember that magnetic field is a vector quantity. Now please check this figure. Now these dotted lines are nothing but the magnetic field lines. These dotted lines are known as magnetic field lines. What are their properties we will study. Before that, please note and put a star mark to this definition, which states that a magnetic field line is a continuous curve in a magnetic field such that the tangent at any point of it gives the direction of the magnetic field at that point. Meaning that whatever magnetic field lines we see here, at any of the lines, if we draw a tangent means a perpendicular or 90 degree, then that is the direction of the magnetic field at that point. Now let's talk about the properties of magnetic field. First of all, as you can see from the figure, they are closed and continuous curves. Outside the magnet, they are always directed from the north pole towards the south pole, and inside the magnet they will be directed from the south pole towards the north pole. Outside is north to south, inside is south to north. So a closed and continuous loop is formed. Then the tangent at any point of the field will give us the direction of the magnetic field at that point, basically this point. This point number 4 is very important. Two magnetic field lines can never intersect each other. Why? Because if they intersect, that will mean that we have two different directions of magnetic field. Now that is impossible. Now point number 5 says that near the pole, be it north pole or south pole, the magnetic field lines will always be crowded, and since they will be crowded, there will be a strong magnetic field near the poles. But in the middle of the magnet, towards the middle of the magnet, these field lines will be far more separated, and this will result in a weak magnetic field. Point number 6 is, when we see a parallel and equidistant field lines, then that means a uniform magnetic field. And if the lines are not parallel or equidistant, that means the magnetic field is non-uniform. And finally, they behave like stretched elastic rubber string, the rubber strings that we use in our day-to-day life. Now out of these 7 points, that is the properties of a magnet, you are expected to remember at least 4 to 5. Now, magnetic field of Earth. We know that Earth also behaves as a magnet. How can we prove it? From these 4 points, at least keep 2 points with you. First one is, if we suspend a magnet, then that rests along with the geographic north and south direction. The first figure with which we started our discussion. And if we happen to place an iron rod inside the Earth along north and south direction, then after some time that iron rod, which is buried inside the Earth, starts to behave as a magnet. Okay, and how we can get the neutral points? By plotting field lines of a magnet where the magnetic field is 0. Now, plotting of these field lines we will be doing in experiment, so I am not going into so much of detail into this. Now, the points that we had discussed there, see in these figures, the field lines are coming outside the magnet. They are coming from North Pole and going towards the South Pole. They are coming from the North Pole and going to the South Pole of the magnet. If we have two different magnets, then also it's coming from the North Pole and going to the South Pole. Coming from the North Pole towards the South Pole. If we have two like poles, then they are not going towards each other, rather they are repelling each other. Now, we have to understand what are neutral points. Now, neutral points basically is a point within the magnetic field where the net magnetic field or the effect of the magnet is 0. If a compass needle is placed at the neutral point, it will rest in any direction because there is no presence of magnetic field. Okay, so please mark this as important, the definition of neutral points. Now we come to the second part of the chapter, that is electromagnet and its uses. Now here we just are expected to know the definition and some of its uses. So we will try to do it in a brief manner. We'll not go into much of details. Now, what is an electromagnet? Basically, electromagnet is a magnet that we have made. It's not a natural magnet. How do we make it? We take a iron or a steel bar and we wound it with copper wires. Then what we do is we pass electric current through it. As if you remember, we said that through electricity also we can produce magnetism. This is what we are doing in case of electromagnets. So the definition of electromagnet says, an electromagnet is a temporary strong magnet made from a piece of soft iron. When current flows in the coil wound around it, it is an artificial magnet. Why do we need an artificial magnet? Because the natural magnet that we have had got two limitations. One is it has got odd shapes, uneven shapes, which are not of so much use to us. And secondly, the magnet is not very strong. That is why we can't rely on the natural magnet. We have to have man-made magnets. So, as you can see, the electromagnets are of two types, the I-shaped or the bar magnet, and then we have U-shaped or horseshoe magnet. How do we construct I-shaped electromagnet? You can see we have taken a PQ, which is a soft iron bar. We connect it from a battery through an ammeter and rheostat. Then we have a key and we connect it in this manner. From the positive terminal of the battery we connect to side P. Now once the current is switched on, since at side P the current is going in clockwise direction. That is why side P develops or becomes as south pole of the magnet, because the current is going in clockwise direction, and the side Q becomes the north pole because the current here, the direction of the current here is anti-clockwise. So this is how an I-shaped or a bar electromagnet is made. Again, this acquired the magnetic property because of the electric current. So this is also a temporary magnet. Now, how do we construct U-shaped electromagnet? Check the figure again. Here, we take the soft iron core, but not in form of a bar, but in the shape of horseshoe. Now again the setup is the same. We connect the positive to side P, and again here the current is going in clockwise direction, so this end will be the south pole, and on the side Q we have the current in anti-clockwise direction, so this becomes as north pole. Now this is how a horseshoe electromagnet is constructed. Now please mark this. These electromagnets are used in DC motor and AC generators. This is very important because it talks about the use. And the I-shaped electromagnet is used for a relay. Now relay is a switching device. Then please put a star mark to this point. How can we increase the magnetic field of an electromagnet? See, there are two ways of increasing the strength of the electromagnet. First, you increase the number of turns, so more current will flow through it and the magnetic field generated would be stronger. And the second point, how we can increase the strength of the electromagnet, is by increasing the strength of the current. If you give more current, then automatically this will have more magnetic field. Now, what is the difference between a permanent magnet and an electromagnet? This is also very important. Now, first of all, electromagnet is made up of soft iron and permanent magnet is made up of steel. Now, steel has got higher retentivity than iron. That is why if the current is switched off, soft iron loses its magnetism, but steel retains its magnetic property, and that is how it becomes a permanent magnet. Now, electromagnet produces current as long as electromagnet produces magnetic field as long as the current is flowing through it, but in permanent magnet there is no such case. It will be a permanent magnetic field. Then the magnetic field strength can be changed, but here we cannot change the field strength. Now point number 4 is magnetic field can be very strong, but for permanent magnet, whatever magnetic field we have got, it will remain and it is not so strong. The polarity of an electromagnet can be reversed. How can we reverse? By changing the direction of the current, but it cannot be done in case of permanent magnet. And point number 6 is it can easily be demagnetized. How do we demagnetize? By simply switching off the current, but in case of permanent magnet we cannot easily demagnetize. Now point number 4, 5 and 6, they are the advantages of the electromagnet over a permanent magnet. Now, what are the uses of electromagnets? This is very important. For out of all the points, you can keep any 3 to 4 points with yourself. Now, for lifting and transporting heavy iron scrap, you might have seen it in movies. And then for loading the furnace with iron, for separating iron pieces from debris and ores, because of magnetic property, the iron pieces will be attracted to the magnet. Then for removing pieces of iron from wounds, this finds the application in medical field. In scientific research also, to study the properties of a substance in magnetic field, whether the substance is a magnetic material or not. And then in electric devices as electric bell, telegraph, electric tram, and etc. Now we will try to know the use of electromagnet in an electric bell, how it works. Okay, this is not in syllabus, but to be on the safe side we will just go through it quickly. Now let's understand the parts of the electric bell. We have a horseshoe magnet, you can see here, this U-shaped or horseshoe magnet M. Then we have a soft iron armature A, armature of iron. This is the soft iron armature A, which is connected to the hammer H. Then we have the gong of the bell, and T1 and T2 are the terminals. Now this is connected to the battery. Then we have the switch, and these are the adjusting screws. Now try to understand how the entire function works. The moment we switch on the current will flow through the T1 and will be transferred to this screw. Now since there is current, the current will flow through this U-shaped magnet. There will be polarity developed. Because of this polarity, this U-shaped magnet, because of the current, it will start behaving as a magnet. The moment it behaves as a magnet, what will happen is this iron armature, which is connected to H, will be attracted towards the magnet because it is made up of iron. So there will be attraction. So it will go and try to hug this U-shaped magnet. The moment it leaves its place and comes forward, this hammer will strike the gong. Now the moment it leaves its position, what happens that the current flow breaks because this is no more connected with the armature S, S and S prime. So the moment current flow breaks, there is no more magnetism here. So again this iron strip will be relieved from here and it will go back and touch this S, S and S prime armature, or you can say the adjusting screw. So the moment it gets back to the adjusting screw, again there is a current flow. The moment there is a current flow, there is a magnetic field. When there is a magnetic field, again this will be attracted towards the magnetic field and the hammer will strike the gong. This is how the electric bell works. Thank you.